Good morning, my good students. This is Dr. Morgan at Clovis East High School. Let's begin today with lesson 8.3. We're going to be exploring exponential functions, how to evaluate them, and how to graph them. A quick definition from our vocabulary. Notice that an exponential function is a function that repeatedly multiplies an initial amount by the same fixed number. You see it has the form of a equals a times b to the x, where b is greater than 0 and b does not equal 1. For an example on the right there, y equals 3 times 2 to the x. That means we start with an initial value of 3 and we continue to multiply it by 2. That's what we saw in the geometric sequence, but an exponential function is actually a continuous line, as we're going to discover. Let's begin by looking at the shape of exponential functions. The general equation is y equals a times b to the x, but I want you to notice how the shape changes depending upon what numbers we put in for a and b. In your typical case, if a is a positive number, in other words it's greater than 0, and b is bigger than 1, we get a graph that looks like a. Notice we're taking the number 2, that's our initial value, and we're going to multiply it by 3 each time. So each time I multiply by 3, it gets bigger and bigger and bigger. So from left to right, it's curved, increasing upward more and more. But let's take the same function. We're going to keep a equal 2. In other words, a is still be 0. But this time we're going to let b be between 0 and 1. In other words, it's going to be less than 1. It's going to be a fraction. So in this case, I make it 1/3. Now what we're multiplying it by is 1/3. That's the same as dividing it by 3 each time. So this time my function from left to right is going down because it keeps getting smaller and smaller. On our next slide, we're going to see what happens when we let a be a negative number. Now in these two functions, notice that a is a negative number. It's less than 0. Now when b is greater than 1 like before, for example here, if y is minus 2, that's where I'm at when x is 0. But this time it's a negative number, so as I'm multiplying it by 3, it's going down because negative numbers are going down on the y-axis. On the other hand, if a is less than 0 and this time I am multiplying it by a fraction, in this case minus 2 times 1/3 to the x, in this case you see that it goes from left to right going up, but it never gets to be a positive number. So let's look at first at evaluating exponential functions. Our first problem, we have 30 flower beetles that are left undisturbed in a warehouse. The beetle population doubles each week. So the function for this production is f of x equals 30 times 2 to the x. Notice that the amount of beetles we start with, 30, is our a, and then it's doubled, so we multiply it by 2, and then we do that every week for x weeks to give us the population. Now we want to find out how many beetles are there going to be after 56 days, or in other words 8 weeks. Well, first thing to remember, we're not going to put 56 in the equation because the equation is for weeks. So we have to figure out how many weeks is 56 days. Well, 56 divided by 7 days in a week means 8 weeks. So that's the number we're going to put into our equation. So the population after 8 weeks, f of 8, is going to be 30 times 2 to the 8th power. Now how do we find this? Well, you could just go 2 times 2 times 2 times 2 times 2, 8 times, but exponential functions is one of the places that our calculators come in handy. Most of your scientific calculators are going to have your exponent keys either going to be the caret symbol or maybe x to the y or y to the x. In this case, I'm going to type in 2 and then push the caret button or the other function, 8 and equal, and I'm going to find out that 2 to the 8th power is 256. Now I multiply that out and I get 7,680. As a result, I can conclude that after 56 days or 8 weeks, there will be 7,680 beetles in the warehouse. So let's try this again with rabbits. We did this earlier in the year. We're going to start with 20 rabbits, and they triple every half year. So the function is f of x equals 20 times 3 to the x. And this gives the population after x half years. So it starts with 20 and triples every half year or every 6 months. How many rabbits will there be after 3 years? Again, we have to remember the function is for half years, so 3 years is how many half years? Well, 3 years is going to be 6 half years. So now we can plug in and find f of 6, the number of half years. 20 times 3 to the 6th power. Again, when you bring out your calculator, you can use one of these 3 keys, and so we would punch in the first number 3, and then whatever symbol we use, the caret to the 6th power is going to equal, and we find that 3 to the 6 is 729. So after 6 half years, or 3 years, there's going to be 14,580 rabbits after 3 years. Now let's look at how to graph an exponential function. The first thing we want to do with the graph is to make a table of values. We're just going to pick different values and then line them up together. So then after we do that, we evaluate the exponential function to find the y values. So we'll pick values of x depending on our problem. It could be all positive, 0, 1, 2, 3, 4, 5, or if we do want to know negative numbers, we can start back at, -3, -2, up to +3, something like that. And then we plot the points from the table and connect them with a smooth curve. So in our first example, we're going to find the graph of the function y equals 3 times 2 to the x power. At x equals 0, its value is 3, and it's being doubled every time. So we've made our table with our x. Notice I've picked negative and positive values starting at -2 up to 2. And now we simply plug them in and evaluate them. So when x is -2, that's 2 to the -2. Remember that the negative exponent means I take the reciprocal of the base, becomes 1/2. So 1/2 positive squared. So 1/2 squared is 1/4. So 3 times 1/4 is 75 hundredths. Let's do it for -1. And there's by the way, there's my plot there, 2 and about 0.75. You have to estimate it there. Now for -1, 2 to the -1 is 1/2. So 3 times 1/2, or 3 divided by 2, is 1.5, and then we come over here to 1 and graph it. And now to the 0 power, any number to the 0 power is 1, so 3 times 1 is 3, and we put that on our graph. Notice when x is 0, that's our initial value, 3. When x is 1 now, we have 3 times 2, or 6, plot the point here. And then when x is 2, 2 squared, 2 times 2 is 4, 3 times 4 is 12, plot the point, and now we try to draw a curved line through it. And that's our problem. And by the way, this is what that function looks like if I graph it in Desmos. Okay, Desmos is an easy way to see your graph. By the way, Desmos, when you're putting in the exponential, it uses the caret symbol to find that, to evaluate the exponent. All right, let's try it for problem 4. Here our beginning value is 1/4. In this case, it's the value when x is 0, and we're going to double it each time. So let's try it first for, again, we set up values of x. I set them from -2 to +2. For -2, 2 to the -2 is the reciprocal, 1/2 positive squared. 1/2 squared, 1/2 times 1/2 is 1/4. So we actually end up with 1/4 times 1/4, 1/16, or I'm going to put it in decimals because it'll be easier to kind of estimate it on our graph. So let's put our first point in there. Kind of tough to do, but at -2, we're at 0.0625, real small. Let's do it for x equal -1. 2 to the -1 is simply the reciprocal, 1/2 to the +1, or just 1/2. So 1/4 times 1/2 is 1/8. In decimal, that's 1.125. So there we go. Now when x is 0, 2 to the 0 is 1, so we're simply looking at 1/4, or 0.25. Now when x is 1, we're going to have 1/4 times 2. Well, 2 times 1/4 is 1/2, or 0.5. And then finally when x is 2, 2 squared is 4, so 4 times 1/4 is 1. So there's our next dot, and now the next step, draw the line. Again, here's what it looked like when I typed it into Desmos. All right. Notice it looks a little different than ours because the y scale is squeezed down more in this picture than it was in ours. But it is the function. In the next problem, they want us to complete the table and graph two different functions. If you look at the two different functions, f of x is simply 1/2 to the x power. A in this case is simply 1. This is 1 times 1/2 to the x. G of x is 3 times 1/2 to the x. So notice they want us to just take a look at what happens when my beginning number is larger. All right, so let's start with f of x. We need to evaluate it first. 1/2 to the -2 means, again, the negative exponent, take the reciprocal, becomes 2 over 1, and change the exponent to positive. So I end up with 2 squared, or 4. When x is -1, the reciprocal is 2 over 1 to the positive 1, so that's 2. When x is 0, any number to the 0 power is simply 1. Now we go to the positive integers. 1/2 to the 1 is simply 1/2. And 1/2 squared is 1/2 times 1/2, or 1 over 2 squared, or 1/4. So there's our numbers. Now when we come to g of x, it's real simple. G of x is simply 3 times 1/2 x, or in other words, it's 3 times f of x. So when I want to find the -2, it's going to be 3 times that, so it's simply 3 times what f of x was, 4. 3 times 4 is 12. The next one's simply going to be 3 times 2, and then 3 times 1, and then 3 times 1/2, and then 3 times 1/4, and that becomes our table for g of x. So let's move on to graph it. So here I've put the results of our graph from the previous slide so you can see them, and we're simply going to graph them. So we'll start with f of x. We have -2, 4, -1, 2, 0, 1, 1/2, and 2 1/4. And then we draw our line again. So now we look at g of x. We have -2, 12, -1, 6, 0, 3, 1 3/2, and 2 3/4, and we draw our line. So you see there are some similarities. It's just that the other one is always 3 times bigger. The blue line is always 3 times bigger than the red line. And here is how this would look if I graphed it in Desmos. Desmos gives me the actual nice curved line, not the ones that I try to draw on the computer, which aren't always totally accurate. In problem 6, they're giving us the function f of x equals 30 times 2/10 to the x power. And they want us to find the range for the domain -2, -1, 0, 1, and 2. To do that, all we simply need to do is substitute the values of the domain into the function. So we want to find these values. F of -2, notice I put -2 in for the x. F of -1, I put -1 for the x, etc. And so I'm going to find those two, and that will be my range. Those 5 values match up with the domain. So 2/10 to the -2 is 1 over 2/10 squared, which is 400ths. So 30 divided by 400ths is 750. 2/10 to the -1 is 1 divided by 0.2. So we get 30 over 2/10. That's going to be 150. To the 0 power means just 1. So that's going to be 30. To the 2/10, now 30 times 2/10 is 6. And 30 times 2/10 squared is going to be 1.2. So notice my range now is 1.2, 6, 30, 150, 750. Notice I just simply wrote the range in numerical order from least to greatest, not in the order I got them from the domain. Question: as the values of the domain increase in going from -2 to 2, what happened to my range? Did it increase or decrease? And you can see it went from 750 down to close to 1. So obviously, as the range decreases, as the domain increases. And here's how this function looks in Desmos. Notice again that it starts up high and comes down, it's getting smaller and smaller. And while it's hard to tell, if you look at where it is, when x is 0, where does it cross the y line? That would be the point 30. So let's try this again with this different function. F of x this time is 5 times 2 to the x power over the same domain, -2, -1, 0, 1, and 2. So again, just like problem 6, we're going to substitute the values in. We want to find f of minus 2, f of minus 1, f of 0, f of 1, and 2. Well, 2 to the minus 2 is 1 divided by 2. So that's going to be 1 over 4, and my answer is 5/4, or 1.25. 2 to the minus 1 is going to be the reciprocal 1 over 2, so this is going to be 5/2, or 2.5. 2 to the 0 is any number to the 0 power is always 1, so this is 5 times 1 is 5. And now 5 times 2 is 10, and 2 squared is 4, so 5 times 4 is 20. So my range this time is 1.25, 2.5, 5, 10, and 20. Those are the y values given the domain of x values. Now looking at this one, as x gets bigger, did the numbers go up or down? And in this case, you see the range increases as the domain increases. Notice the difference here was our b was greater than 1, 2. So that's what tells me it's going to go up. Unlike before, the b was a less than 1, a fraction. And here's how it looks in Desmos. In the next problem, we want to explore what vertical shifts do to exponential models, and how vertical shifts translates a graph either up or down the y-axis. So if we want to look at the graph of f of 2x plus 50, one thing we can do is graph g of x, which is 2 to the x, and then add 50 to it. So for example, if g of x is 2 to the x, when x is 0, that's just 1. When x is 1, 2 to the 1 is 2. When x is 2, 2 squared is 4. 2 to the third is 8, and 2 to the fourth is 16. Now if I'm looking and I want to find what's 2 of x to the 50, I just simply take the g of x and add 50 to it. So I end up with 51, 52, 54, 58, and 66. This is showing you how adding 50 to it is just going to translate the whole graph up. Let's look at it graphically and you'll see it more clearly. So here's the tables from the previous slide, and let's graph them. First, let's graph g of x. So we have 0, 1, 1, 2, 2, 4, 3, 8, and 4, 16, and we'll draw our line. Okay. I added a few more points to get it in there. And then let's add 50 to it, f of x, and so we're going to start with 51, 52, 54, 58, 60, and add another couple just to get the graph seeing that. And you see all that's happened is the red graph has moved up 60 because 50. That's what it does when we shift an exponential function. And this is showing you how it looks more accurately on Desmos. Our last problem, number 9, is just like problem 8, except instead of going up 50, we're going to go down 5. We're subtracting 5. So first, let's find out what the values are for y equals 1/2 to the x power. So when x is minus 2, again, the negative exponent means I take the reciprocal. 1 over 2 becomes 2, and I make a positive exponent. 2 squared is 4. 1/2 to the minus 1 becomes 2 to the 1, or 2. Anything to the 0 power is 1. And now we use our positive exponents. 1/2 to the 1 power is 1. And 1/2 squared is 0.25. Now all we do in the next one is take our values for y over here at the beginning, y equals 1/2 x, and just subtract 5. So 4 minus 5 is negative 1. 2 minus 5 is minus 3. 1 minus 5 is minus 4. 1/2 minus 5 is negative 4/2, and 1/2 minus 0.25 minus 5 is 0.475. So let's see how they look on the graph. So I put the tables in from our previous slides, so let's just graph them. First point here on the first graph, negative 2, positive 4, negative 1, 2, 0, 1, 1/2, 2 1/4. All right. Now let's draw a line. There we go. And let's do the second one, minus 2, 1, and we find our graph. And notice all we have there is The blue graph is simply 5 units down from the red graph. That's a shift down 5. And here's how they look more accurately in Desmos. The blue line is simply the red line shifted down 5. If you measured it with your fingers, down 5 each time. All right, I hope you guys have a great day. Be safe out there and keep well.